Welcome to Think Academy's free live stream channel. I'm your teacher, Danny. I'm broadcasting this class all the way from Cupertino, California, and it is now locally 10 o'clock. Today, we will be talking about the world of spinning. We spin all the time. We spin when we're happy, we spin when we're dancing, and we spin whenever we feel like it. But do you know that spinning actually has a lot to do with the universe? How are they even related? Before we jump right into the universe, I have a question for you guys. How many different ways can we spin? There are so many ways how we can spin, right? To answer this big question, it's very important for us to have the ability to categorize. Having the ability to categorize means that we can put the same things into the same categories, the same kind, and putting different things into different kinds. And for here, we need to understand how to categorize spinning. Again, there are a lot of ways how we can categorize spinning. But today, I want to introduce you guys to two different ways of categorizing spinning. The first is that we can categorize by the center of the spin. And the second is that we can categorize by the direction of the spin. So we will talk about these two categorizations one by one. First, let's talk about the center of the spin. What do I mean by the center of the spin? Center of the spin just means that what we are spinning around at. Well, first, I can just spin around myself, right? When I spin around myself, I do a spinning like this. Okay? I'm spinning around myself. What's the other way? If I'm not spinning around myself, then I will be spinning around something else. Suppose I have an imaginary line here, and I want to spin around this line. So what do? I just spin around it, right? I spin around, and the line doesn't change, but I'm spinning around it, okay? So there are two ways how we can spin around. The first is that I can spin around myself, or I can spin around something else. In science and in math, we actually have names for these two types of spinning. If we are spinning around an internal axis, which means that we're spinning around ourselves, then this is called a rotation. So we are spinning around ourselves, spinning around an internal axis. The axis just means the center of the spin. And another way of spinning is that we can spin around something else, right? We can spin around other objects. So that in science and math is called revolution. And revolution just means that we spin around another object. So we spin around another object. We're no longer spinning around ourselves. Again, rotation means that I am spinning around an internal center of the spin. So I'm spinning like this. And revolution means that I'm spinning around another object or another invisible line. Take a look at this picture. Is this guy performing a rotation or a revolution? Again, the only difference between rotation and revolution is the center of the spin. Let's take a look. Where is the center of the spin for this guy? It's here, right? And the center of the spin is inside of this guy. This guy is actually spinning around himself. So the axis, the center of the spin, is internal, is inside of this person. So he's spinning around himself, then this is a rotation, okay? And rotation is when an object spins around itself. Take another look at this example here. Are the cars doing rotation or revolution? Again, what do we look at? The center of the spin, right? Let's look at the center of the spin here. The center of the spin is at the center of this island, which is not inside of any of those cars, right? So these cars are spinning around something else. If we're spinning around another object, then the cars are doing revolution. Okay? So again, rotation means that we're spinning around ourselves, and revolution means that we're spinning around something else. Now, once we get that sorted, let's do a little demonstration. Right in front of me, I have a globe. And let's just take a look. If we're doing a rotation around these poles here and here, what would be a rotation look like? So again, a rotation just means that we're spinning around ourselves, around an internal center of the spin. So we're just doing this, right? We're spinning around this internal axis right here. We're not moving anywhere else. We're just spinning around ourselves. Okay, so we have a rotation like that. What about a revolution? What if this globe is doing a revolution around this invisible line here? How is this globe going to do a revolution? Again, revolution means that we're spinning around something else. Let me just make the invisible line visible. Here I have an iPad stand, okay? And suppose this globe is just doing a revolution around this iPad stand. So a revolution will just look like this, okay? We're spinning around this external object, okay? Easy. Now, what about rotation with revolution? Well, rotation just means that we are spinning around ourselves around an internal axis like this. And revolution means that we need to spin around another object. So while we're doing rotation, we're also spinning around this external object like this, right? Oopsie. Okay, so there we go. We have rotation, meaning that we're spinning around an internal axis, and revolution means that we're spinning around something else. Well, let me just move this out. Okay. So again, those spinning actually has a lot to do with the universe. How are they related? Let's take a look at this video here.
The Earth and its movements. The Earth is the third planet from the Sun. And it has a unique characteristic that no other planet we know has. It's the only one that has life on it. Life of all types, plants, animals. Its average temperature is 15 degrees Celsius, and because our planet also has water and an atmosphere, it is the perfect place for life. Like other planets of the solar system, the Earth moves in two different ways. One is called rotation, and the other is called revolution. Rotation is the movement of the Earth on its own axis. Rotate means to turn, so the Earth turns around a slightly inclined imaginary line that joins the two poles called the axis. Do you know how long it takes to make a complete turn? It takes 24 hours to make one rotation. Think about it for a second. One day, day and night together, lasts 24 hours too. So the movement of rotation causes day and night. Interesting, right? Now let's see the movement of revolution. As you can see in the pictures, the Earth goes around the Sun in an elliptical orbit. That might sound a little strange, but if you look, you'll see it's simply the journey that the Earth makes around the Sun. Do you know how long it takes the Earth to make a complete revolution around the Sun? Well, it takes 365 days. Exactly 1 year. This revolution movement is what makes the spring with its colorful flowers, the hot summer full of fun, the autumn when leaves fall from the trees to the ground, and the cold and frosty winter. So let's remember the two kinds of movement that the Earth makes. There is rotation, which is the Earth turning around itself, causing day and night, which lasts exactly 24 hours, the same as a whole day. And there is revolution, which is the Earth traveling around the Sun, which takes 365 days and causes the seasons. So now you know the movements of the Earth.
Now we know that thanks to spinning, we get to enjoy the day and night on Earth, and we also get to enjoy the 4 seasons on Earth. For the Earth to complete one full revolution, we get to enjoy the spring, the summer, the fall, and the winter on Earth. So every single time the Earth orbits around the Sun for one full revolution, we have 365 days, which makes up of a year. My question for you is, does it always work out like this in the solar system? Are all the planets in the solar system have 365 days as 1 year? The answer is no. So the shortest orbit in the solar system would be on Mercury. For Mercury to have 1 year, it only takes it 88 days. And what about the longest orbit? What would be the longest year in the solar system? That would be on Neptune. And for Neptune to complete one full revolution, which means that for Neptune to have 1 full year, it actually takes up 164.8 years equivalent on Earth. Interesting, right? So for a revolution of a planet to happen around the Sun, we get to enjoy 1 full year. What about the daytime and the nighttime? That depends on the rotation of a planet. That means how the planet is spinning around itself. So for the Earth, we know that we get to enjoy the sunrise and the sunset every 24 hours. But what would be the longest day in the solar system and the shortest day? So the shortest day is on Neptune. It only takes 16 hours for us to witness the sunset and the sunrise. What about the longest day in the solar system? That would be on Mercury. And it takes 1,408 hours to have 1 full rotation, which is almost 59 days. Wow! So it differs drastically in the solar system. And again, the rotation and revolution gives us the day and night and the 4 seasons on Earth. So the revolution means that we're spinning around something else. The Earth is spinning around the Sun. And the rotation means that the Earth is spinning around its internal axis. And it's constantly spinning, and it takes us 24 hours to complete 1 full rotation. The Earth is constantly doing the rotation and revolution for us to function and for us to enjoy the day and night. Now we are done with the center of the spin. Let's have a quick recap. So we know that rotation means that we're spinning around an internal axis. We're spinning around ourselves, just like the Earth is spinning around itself to produce the day and night. So that's called a rotation. We also learned about revolution. And revolution means that we're spinning around something else. And for example, the Earth is spinning around the Sun. And for every full revolution, we get the 4 seasons. Okay? So these are 2 very important concepts. And if you have a paper and a pen with you, please jot down this note here. So I'll give you 30 seconds to jot down some notes here. So this is note time. 30 seconds, okay? So there are two ways how we can describe the center of the spin. First, by rotation, we mean that we're spinning around an internal axis. So we're just spinning around ourselves. And the second is that we can spin around something else. And that is called a revolution. We're done with the center of the spin, moving on to the direction of the spin. There are so many ways how we can describe the direction of the spin, and today I'm just going to teach you one way. Please allow me to introduce you to clockwise. So clockwise just means that we are following how the clock goes. Do you guys have a clock at home? Let's observe how the clock goes. Here we have a clock. We are moving from 12 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then back to 1 again. So the movement goes like this, okay? So a clockwise movement looks something like this. What about a counterclockwise movement? What does that mean? So counter just means that we're going against. We're going against how the clock goes. How does the clock go? Again, we see that we're just moving in this direction. So if we're going against it, what would that look like? Here I have a Think Academy clock. Oops, upside down. And here at Think Academy, everything are in numbers, and we need to calculate them. Those are easy calculations. We have 6 times 2, which gives us 12. And then here we have 1, 2, 3, 4, 5, 6. It just goes exactly the same as any other clock. But these are just in calculations, okay? So this is just a normal clock with a lot of calculations on it. And if you are at Think Academy's campus, you will see a lot of things are in numbers, okay? So first, let's just look. If we are just moving in clockwise movement, we'll do something like this, okay? So we're moving from 12 o'clock to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, back to 12, and then to 1, 2, 3, 4, 5. And so we just go like this. This is a clockwise movement. What about a counterclockwise movement? We're just moving against how the clock goes, right? So we just go from 12 to 11, 10, 9, 8, and then decrease to 1, and then back to 12 again. So we're just going against how the clock normally goes, right? So a counterclockwise movement just look something like this. Oops, my clock just dropped. Okay, so again, a clockwise movement means that we're going along how the clock goes. And a counterclockwise movement just means that we're going against how the clock goes. Now my question for you is, before the clock was invented, this type of the direction has already existed. What would the ancient human describe this type of movement before the clock was invented? Think about this question. And before we answer this question, let's take a look at this video and let's understand how the clock was being invented.
A lot happens in 24 hours. Your heart beats around 100,000 times. 150 to 200 species of animals become extinct. Lightning strikes Earth 8.6 million times. Astronauts aboard the International Space Station will see 16 sunrises and 16 sunsets. About 367,200 babies will be born, and about 151,600 people will die. So yeah, a lot goes on in just 24 hours. But why is a day divided in 24 hours in the first place? Who decided how we would calculate it? Today, time is tucked away in our pockets, just an unlock button away. It drives our technology, with atomic clocks being responsible for precise GPS location services and speedy internet search results. Our ancestors, on the other hand, didn't have it that easy. Time for them was written in the stars, in the sunrise and sunset, in the moon's waning and waxing. So, how did we go from looking up to celestial bodies to looking down at our phones for time? What other timekeeping methods did ancient humans use before watches and clocks became ubiquitous? And what the heck is an atomic clock? You're watching Explore Mode, and today we're diving into time and how humans developed technologies to measure it. Let's start with celestial bodies. Early civilizations like the Egyptians used the moon's phases to determine the length of a month. In prehistoric Europe, humans built stone rings called recumbent stone circles that would frame and track the moon in each of its phases. It's believed they were built for ritualistic purposes. Then we have the creation of the sundial, a device that shows the time using the sun's shadow, depending on its position in the sky. The earliest archaeological evidence of a sundial was found in the Valley of Kings in Upper Egypt in 2013, and it dates back to 1500 BCE. A larger version of the sundial is the obelisk, which was used to mark the summer and winter solstices. While Egyptians, Romans, and Greeks were using sundials to keep track of time, people in Asia were using candles and incense sticks. Candle clocks worked as follows. Each candle had markings on its sides indicating the passage of a certain period of time, so as the candle burned, you could calculate how much time had expired. The first reference to candle clocks dates back to 520 AD, in a poem written by Chinese thinker You Jiangu, who seemed to use them for study sessions. Similar to candle clocks, early evidence of incense clocks takes us back to China, 6th century China to be exact. Different incense sticks would indicate the passing of time depending on how quickly they burned. Some sticks had different aromas for each hour that passed, and others had weights attached at different sections that would drop as the incense burned. But incense clocks stuck around well after we had developed watches and pendulum clocks. Until 1924 in Japan, geishas would count how many incense clocks had been burned during their services to charge their customers. Egyptians divided their sundials into 12 parts for each hour of the day, from dusk to dawn. Although sundials were quite accurate for their time, they had one very evident disadvantage. They were practically useless during overcast days and at night. But back to the 12-hour day division. So 12 hours for daytime, 12 hours for the nighttime. That's 24 hours a day. No surprise there. But why then is each hour divided into 60 minutes and each minute into 60 seconds? Well, that has to do with a numerical system that is still used today. Time for an Express Explorer explanation. Start the clock. The sexagesimal system takes us back to ancient Mesopotamia. It is a numerical system based on the number 60 that was developed by the Sumerians and later adopted by the Babylonians. They developed it by dividing parts of their fingers into single units and units of 12. Here's how it worked. Take a look at the palm of your hands. Notice that each of your fingers is divided into 3 sections. Using their thumbs to count, the Babylonians realized they could count up to 12 for each section on each finger of one hand. 3 times 4 equals 12. The 5 fingers on the other hand each represented a dozen, so 12 times 5 equals 60. Also, 60 is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Making it an easy number to split for a civilization with no calculators. This system is used nowadays to divide time, angles, geographical coordinates, and it is the mathematical base for astronomical coordinate systems. In order to bypass the no sunlight conundrum, the Egyptians needed another method of timekeeping, and so they developed the water clock. Here's how they worked. Egyptians would fill a bowl-shaped container with water. Said water had a spout at the bottom which would allow for water to flow out into another container. It had 12 markings on the inside, each line representing the passing of an hour. As the water flowed out, they would compare the water level with the markings to determine how much time had passed. The problem with this type of water clock was that it didn't provide an accurate representation of the passage of time. You see, as the container emptied out, the pressure of the water would lessen, making it run more slowly by the end. Enter Ctesibius, an inventor and mathematician from Alexandria, and the man now regarded as the inventor of the first real clock. Between 270 BC and 500 AD, he figured that instead of measuring time based on the outflow of water, he would measure the consistent inflow of it. It worked pretty much in the same way, except that instead of measuring how much a container had emptied, he would measure the rise of the water level as the liquid steadily flowed into the container. Unbeknownst to Ctesibius, he had created the first, albeit quite rudimentary, mechanical clock. For many years, the perfected water clock was the most accurate timekeeping device. That is, until proper mechanical clocks appeared. The first people to build large mechanical clocks were Catholic monks. They needed precise timekeeping devices to schedule chores and prayers within the monastery. According to historian Thomas Woods, the first recorded clock was built by the future Pope Sylvester II for the German town of Magdeburg around the year 996. Then came the inventions of Christian Huygens, a Dutch physicist, mathematician, astronomer, and inventor who, using theories from none other than Galileo Galilei, created the technology behind the pendulum clock and the springs in the pocket watch. Pocket watches were the first to be mass-produced, allowing everyone and their mother to be able to keep time in their pockets. Clocks today are more precise than they have ever been. Seconds are no longer measured with the swing of a pendulum. They're measured with crystals and atomic particles. Time for an Express Explorer explanation. Start the clock. With pendulum clocks, one swing of the pendulum equates to 1 second. This is how you calculated time. But pendulums depend on a lot of external factors to maintain a constant swing, so a more precise form of frequency was needed to create more accurate clocks. That's where the quartz comes in. Check your wristwatch or whatever timepiece you own. If it says quartz, it means that your device is powered by a crystal. The quartz is a clear mineral made of silicone and oxygen that vibrates at a very precise frequency whenever it is zapped with electricity. Quartz crystals are fashioned into resonators in the shape of a tuning fork and put inside timepieces where they're receiving constant electric signals. A piece of quartz resonates at 32,768 pulses per second, indicating that whenever the quartz reached that amount of pulses, a second had passed. But although quartz clocks are fairly accurate, they're still not the most precise form of timekeeping. Quartz crystals vibrate at different frequencies, depending on whether they're in warm or cool environments, making them gain or lose a few seconds. What can be more precise than the oscillation of a crystal being electrocuted? Atoms. Cesium-133 atoms, to be precise. See, cesium atoms resonate between different energy states at an extremely stable frequency, a quality that is imperative for precise timekeeping. So, in 1967, the National Institute of Standards and Technology declared that the official measurement of a second is equivalent to 9,192,631,770 oscillations of a cesium atom's resonant frequency. And that is still the standard used today. Timekeeping devices nowadays not only help us determine our work schedule or set up our alarms, they're an integral part of the technology we see all around us. GPS satellites have at least 2 cesium and rubidium atomic clocks on board in order to calculate the time delay of signals and provide an accurate reading of a location. In December 2018, scientists at the National Institute of Standards and Technology developed 2 clocks using 1,000 atoms of the element ytterbium in grids of lasers. These clocks are so precise that they can show the effects of gravity on Earth, helping us measure the space-time continuum. So far, this is the most precise form of timekeeping, but a new technology might emerge in the next decade, or century, or millennia. Who knows? Only time will tell.
Now we know that the ancient human used the water flow, the incense, the sun to measure time. Time is a really special concept because we don't touch it every day, and we don't see it every day. But we know that time flew away from us just by looking at the movement of the sun. When we have sunrise and sunset, we know that one day has gone. Back to my original question. Before the clock was invented, how do people describe the movement of clockwise? People actually use sunwise to describe clockwise because the clock is actually mimicking the movement of a sun. The sun has been the center of the story for today. It gives us the 4 seasons, it gives us the sunrise and the sunset, and it also gives us a concept of time. So thank you, sun, for giving us all the things that we enjoy on Earth. Let's have a quick summary. Today we learned about spinning. And we know that when we learn about a really, really big concept. We need to start from a smaller thing. So we categorize spinning into two different kinds. We can categorize spinning by the center of the spin, or we can categorize by the direction of the spin. When we're spinning around ourselves, what type of spin is this? It's a rotation. And when we're spinning around something else, what type of spinning is that? It's a revolution, okay? So the rotation of the Earth gives us 24 hours, and the revolution of the Earth around the Sun gives us the 4 seasons. Now, moving on to the direction of the spin. We have two types. The first is that we go around how the clock goes, and that's clockwise. And the second is counterclockwise, which means that we're going against how the clock goes. Again, two types of center of spin. The first is rotation, where we spin around ourselves. And the second is that we spin around something else. That's revolution. And we can also describe a spinning by its direction. The first is that we can spin according to how the clock goes, clockwise movement. And the second is that we're going against how the clock goes, counterclockwise movement. So now we can just describe any kind of spinning with these two types of categorization. Let's look at 3 pictures here. First of all, we have 2 kittens, and they're spinning. Let's decide what type of spinning is this. What's the center of their spin? Are they spinning around themselves or something else? Well, they're spinning around an external center here, right? So if they're spinning around an external center, what type of spinning is this? This would be a revolution. All right. So we know that because the center of the spin is external, this is a revolution. Now, what's the direction of their spin? There are 2 kittens. We can just look at one of the kittens and trace its movement. Let's do this. Should we pick the red kitten or the brown kitten? What about the brown one? Let's do this. We'll just follow how the brown kitten is moving. And look, we're moving in this type of direction. So is this clockwise or counterclockwise? Look at your clock. This is a clockwise movement, okay? So we're doing a clockwise revolution. We're following how the clock goes, and these 2 kittens are moving at an external center. All right, so now we know how to describe these 2 kittens. Let's look at the basketball here. We're spinning a basketball. Where is that center of the spin? This is an internal spin, right? We're just spinning around the basketball itself. So this is a rotation. Great job. We're spinning around ourselves. Now, moving on to the Kirby here. Do you guys play the Kirby? She's so cute, right? Okay, so what type of movement is Kirby doing? Is she spinning around something else or itself? Itself, right? Its center of the spin is right across itself. So what type of spinning is this? Rotation. Great job. Again, if we are spinning around ourselves, then that will be a rotation. And if we're spinning around an external center, that's a revolution. Okay. movement is Earth doing? Do you still remember? Well, first of all, the Earth is spinning around the sun. What type of movement is this? Revolution. And secondly, the Earth is also spinning around itself. So what type of movement is that? Rotation. So the Earth is both doing a revolution and a rotation. All right. Now let's do a happy spin. Yay! Because the class is over. But before you guys leave, one last question for you guys. What type of movement is this? This is a rotation, right? And which direction is she spinning? Well, looks like something like this. Okay, so we're spinning like this. What type of direction is this? A counterclockwise movement. So here we have a counterclockwise rotation. During this coronavirus breakout, we actually have a lot of really fun things for you guys. So today we have gone through our live stream channel. Besides our live stream channel, we actually have a really fun courses prepared for you guys, which is called the Basic Mathematics. And we break the classes into 3 levels. Some of the classes are really interesting. For example, the clockwise and the counterclockwise rotation, which is essentially building on what we learned today and have a more advanced knowledge in terms of how we can spin. And we will also learn about the number patterns, which is essentially the different types of number patterns. For example, the arithmetic sequence, the Fibonacci sequence, and we will go over a little bit of the number sequence later on in our next class. And we will explore the sequence in numbers. So stay tuned for our free live stream channel and also the really fun and interesting class. And this class is designed for the entire May. So we will have 1 class for every Mondays, 1 class for every Wednesday, and 1 class for every Friday. So 3 classes for each week, and that's for the entire May. If you are interested in the class, feel free to scan the QR code with your camera, or you can email us and visit us at our website. Right, thank you so much for your time today, and I hope to see you in our next free live stream class, which will happen in around 15 minutes. Okay? See you guys soon, and I hope you guys enjoy it. Bye-bye. Stay healthy.